It's loading. Okay, and we're live.
Okay.
Welcome everybody. Today we're very lucky to have Sofia Brookie here to tell us about her master's thesis work on egress modulo theory, which, as we were just discussing, is an exciting and a hot topic. And so it's great to see someone really diving in and fleshing it out. So I'm excited to hear what you have to say today. Take it away.
Okay. Yeah. So I'll start with a brief overview of sort of the structure of egress. There's really sort of three different layers, right? At the bottom we have this union find. On top of that we sort of have a congruence closure, and on top of that we have this equality saturation layer. And you can see them as sort of handling different strengths of theory. So the union find just handles ground atomic equations, like E1 is equal to E2. Is everything okay?
Yeah. So
Okay, cool. Sorry, I just heard something. Yeah, and then the congruence closure handles the non-atomic part, sort of building on top of the union find, and then equality saturation handles the really difficult part, which is non-ground equations, which I call identities to not confuse them with. I call these equations and these identities typically. And this is the thing that's not really in general decidable. You just put in some of the identities and hope that you can't. It's hard in general to prove that a saturation will terminate. So now associativity and commutativity, very common identities. I haven't got the quantifiers here, but hopefully that's clear enough. And in particular, I'm focusing on AC for reasons that I will get to a little bit later. And so egress tend to struggle with AC operators or similar operators, ACU, which is AC with a unit, or abelian groups. And I'll just, in general, just use plus as sort of a generic name for AC operators in this talk. So there's sort of A plus B represented as an E graph. If you go to size 3 and you want to represent, you have to represent these reassociations and recommutations, right? So that's at size 3, that's at size 4, that's at size 5. Obviously, it's getting quite a lot bigger, even for just a term that is that might actually be size. Oh, I don't know. Maybe it's cut off. Anyway, but that's if you go a little bit bigger. Here's just a small window of something of like size 8, right? So you have all these nodes that are. You don't just represent, and the top node has to represent all these different ways to split it up into 2 pieces. But then you also get all these lower level nodes. And this is obviously if you run to saturation, doing as many steps of associativity and commutativity as you can. You get a lot of E nodes in a lot of E classes with a lot of E nodes in each one. So yeah, blindly saturating with A and C gives 2 to the E classes, and each one has order of 2 to the N E nodes in it. So it's doubly exponential in size if you run to A saturation under AC. So with A, it's only cubic, which is one reason not to focus on it. If you don't have any cycles in the graph, then it's only cubic. If you do have cycles, then you get then you can't actually hit saturation because there's no way to represent the infinite set of reassociations of a cyclic term under associativity. But also making progress here is hard because A is fundamentally undecidable, which I will mention again, sort of why, in what sense it's undecidable. So non-solutions that have been used, or solutions or non-solutions that have been used in the past to deal with AC, you can use a back-off method. If a rule is used a lot, if you use associativity too many times, you just sort of lower it in the priority list and use it less and less and hope that sort of resolves the issue. There's some issues with this. It doesn't help if you want to run to saturation anyway, because you're going to have to do all the steps regardless. And it can slow down finding if you want to find some particular equation, having some back off might mean you miss the associations that you actually need to use to get to the equation that you want to show, that you want to derive from your input. And so here's just a sort of brief examples using associativity and commutativity. There's some function satisfies its identity, which is basically what you might imagine for an affine function. And you want to go from the starting term to this final term using this thing, which and here's just the example using the online equal demo. it times out pretty quickly. You see it's done all these sort of, it's done lots of associativity and commutativity steps, but it hasn't sort of gotten, there's only a couple that are actually needed to show this, that this equals this, but it sort of got stuck just doing commutativity and associativity steps. So the set people have added that have thought a lot about this idea of theory-specific solvers. So that's at least, as far as I can tell, the motivation for calling it egress modulo theories. And so the idea is, can we handle AC? The question is, can we handle AC in a specific way rather than relying on this sort of very generic equality saturation that just sort of keeps running in a loop and adding E classes and E nodes? Yeah, so this has been thrown around for a while. Philip Zucker's mentioned it a few, and I've seen other people mention it. There's a few details that need to be ironed out to actually make it work, which is what I'm going to get into in this talk. So yeah, so here's our example that I used with this F thing. Instead of representing binary plus, we sort of think of it as an n-ary operator, right? And we don't, and we would just, not represent any associations or commutations. We just think of it as magically somehow up to commutativity and associativity. And then the final graph at saturation, if we could pull this off anyway, would look something like this, right? It's a fair bit more compact. We don't have to, so this is the ideal, and we'll get to how to actually do this, or whether the extent to which this is feasible. But that's the idea, is we want to just sort of represent things up to associative and commutative. You see, we still sort of do end up having quite a few nodes, but it's that's the hope anyway. So just a couple of notes for things that sort of inspired this work. Egress connect very closely to the theory of rewriting. And congruence closure is very similar to ground Knuth index completion. And then the other connection for egress is they're closely related to tree automata. I won't go into these connections in depth, but so some sort of inspirations for the modulo theories idea. There's a well-defined notion of rewriting modulo theories, and there's also a reasonably well-defined notion of doing automata modulo theories, like tree automata, except the trees are non-free in some sense. Okay, so sort of digging into what the problem with egress is, why do they handle this AC so badly? So the way egress work in general is that they add a new symbol for everything. Well, if you have f of E1, if we haven't seen that before, give it a new E class, aka a new tree automata state, if you want to think of it like that. So, right, and so if we have a term that is in multiple E classes, we ought to merge the E classes, right? And this is what rebuilding does. And so there's only a couple of very basic cases of overlap that we hear about. The first is when you have f of E1 and E1 rewrites E2, right? And f of E1 rewrites E3, then we should sort of change this so that f of E2 rewrites E3. That's a parent-child overlap. The other kind is this sort of self-overlap, where f of some term rewrites to two different things. So to handle sort of a general grandchild overlap and so forth, you could just iterate these very basic kinds of overlap check, and that's basically the egress algorithm. So that simplifies confluence, because if you have a critical term, if you have a critical pair of terms, as in a term that could, egress is presenting a rewrite system, right? So if you have a critical pair term that could rewrite two ways, there's only a few ways that could happen, and you do the overlap checks and you resolve them by setting certain things to be equal, and then so this notion of critical pair is sort of the key notion that we're going to have to generalize to do congruence closure modulo T properly. We need to find critical pairs and resolve them. Find critical pairs modulo T. And
Sophia, I have a quick question.
Sure. Sure.
So I think I'm following sort of like the general notion of why critical pairs are like, we're setting up some analogies to, rewriting and completion, and that feels good. I also think I understand the way in which you've sort of framed congruence,
Yeah,
closure, or rebuilding as a very simple um, rewriting system. I guess, can you
yeah,
just
yeah,
say a little bit more, and you maybe already said this, but maybe say it again, um,
yeah.
on what, like, from, like, congruence closure is clearly a very limited rewriting system,
Mm,
right? Like, there's
yeah,
only
yeah,
certain kinds of rewrites. And so, like,
yeah, yeah.
what are the critical pairs, and what way are they limited? Like, what is the structure of those critical
Yes,
pairs?
yes. Okay. Um, so the two kinds of rewrites. The first is atomic rewrites, like E1 to E2, which is
Hmm.
handled by the union find, right? This is E1 is E2 as a ancestral parent in the union find, right? And
Mm.
the second one is this one. F of some atoms, including E1, say, rewrites to E3. Sorry, just need a drink.
Okay.
So yeah, so these are basically the two kinds of rewrites you can have. The first is like purely atomic, and the second one is rewrite a single layer of the term with atoms in the leaves to another atom. And so the two kinds of critical pairs are either this, oh, oops, this directly overlaps with this in the sense that you have this rule here and this rule here, and you could rewrite this in two ways. One is to E3, you could rewrite f of something, something, including E1 to E3, or you could rewrite the E1 inside to E2.
Mm.
So you get f of blah, 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 E2, dot, dot, dot. That's the critical pair in that case. And the other kind of critical pair is when you have a direct overlap, right? You have the exact same thing here that can rewrite it to two different things. One is E3, one is E4.
Right.
Those are the
Okay.
two kinds of critical pair.
Okay.
Does that
Great.
clarify
Yes. Thank you.
the critical pair situation? Yep. Okay. And so yeah, the handling what would be more complex kinds of critical pairs is done essentially by fixed point propagation, right? You flatten the terms into these sort of very atomic rewrite steps, and then handle the critical pairs of those. So then we look at the notion of AC critical pair. So here's an example, right? If you imagine, we'll just think of equations rather than rewrites for now, but if you look at these, B plus C is sort of the overlap of these two terms, right? Except it's not a direct subterm overlap because they don't both contain B plus C, but it is sort of implied that there's this overlap between them. And you can develop this critical pair based on this, that E1 plus D would be equal to A plus B plus C plus D, which would also be equal to A plus E2, right? So what is sort of AC? What is equality saturation doing with AC? Well, any of the sort of O to the 2 to the n AC subterms could become an AC critical pair, right? So equality saturation doesn't have any sort of smart way of figuring out in advance whether something could become a critical pair or not. It just sort of finds everything and adds it to the E-graph as its own thing. Yeah, so equality saturation only sort of grounds identities. There's no sort of special mechanism to wait until something is needed to ground it or anything. It just sort of grounds everything it can see. So just
Sorry, I have one
yeah,
quick
sure.
question, and maybe you're going to get to this, but I agree with you
Mm,
100% that equality saturation is very straightforward and simple in the way that you
yeah,
described.
yeah,
It has no way of knowing what is needed. I guess
mm,
what is needed is a very tricky
yeah.
notion. Is that something you're going to
Um,
expand on? The notion of what's
so
needed?
yeah, there's I mean, I guess there's like maybe a slightly better notion of what is needed if you if you focus on AC, right? Uh, it's only these AC critical pairs that are needed in a sense, right? Which you can discover by sort of going through and actually directly finding the critical pairs by like analyzing the overlap. I guess maybe you could do this in general, but I don't know. I mean, I don't know if that's a general method. But anyway, I would get to a actual method for doing AC that is. So maybe this is a bit of a strange way of presenting. I just want to kind of motivate why it is possible to do better than equality saturation.
Okay.
Yeah. So existing suggestions for making some sort of egress modulo theories. Well, one idea is to canonize the sort of T parts of the graph. So you associate everything to the right, say, or sort, order the nodes by flipping them if they're sort of unordered in the wrong order or something. The other, and both of these are very similar. The other idea is to treat nodes as containers in the sense of like lists moving from fixed arity function symbols to lists of E-class names to bags of E-class names and so forth. And so working modulo A possible with units is like the theory of semigroups or monoids. It's like lists, also associated to the right. ACU is like commutative semigroups or like bags or like sort ascending and associated to the right. And these are the basic correspondences between these notions, right? So why do we need all these AC equivalent ways of representing the same thing? Can't we just pick an AC representative? That's the idea of both of these, really. And so that, yes, but you do need some method of finding the critical pairs mod T, basically. And to make a complete algorithm, you have to sort of eventually resolve every critical pair in some way. Also, there's the problem of matching, but I will not talk. I don't think I'm going to talk about matching much in this talk. So, I mean, here's a very simple example. Modulo A, this sort of has an infinite set of implied subterms B, B plus B, B plus B plus B. Because you can imagine taking A, rewriting it to A plus B, rewriting that A to A plus B, and so forth, arbitrarily many times, and reassociate to get as many Bs as you want. So this is sort of one failure case for what I call prehistoric methods of EMTs, these sort of vague ideas that you could just canonize things, right? I mean, here's another, is that if you only work modulo A, the infinite set of equivalent terms becomes this set, which is now not regular, so you can't represent it with a tree. You can't recognize it with a tree automaton. So it's a fairly easy to prove that there's like no E-graph that can represent all the reassociations of that in a compact way, unless you move beyond this sort of tree automata level of strength, I guess. Here's another example. All these equations are individually canonical, but then there's this. This is sort of more to an example that's more to the point. We've got this consequence that we like to derive from these, but they're all individually canonical, but sort of together they're not canonical because there's this missing. There's this missing. This equation that is sort of implied that is missing, right? D and F should be identified. So just canonizing like individual pieces of the E-graph doesn't mean doesn't get away from the problem that you need to sort of scan for implied equalities. And sort of one insight is that this is a known problem. It's the same as what is known as the word problem in algebra, or so any mechanism to resolve all T critical pairs is a solver for the T word problem, right? So A does not have a decidable word problem. AC does, so that's sort of the key connection. I mean, that's one reason to focus on AC rather than A. I mean, there are some things you could do for egress modulo A, but you're never going to have as nice a solution because it's not fundamentally a decidable problem. Yeah, so as I said, there's no package solution for just the A word problem because it's undecidable. So you can provide a list of critical pairs to the outer loop of equality saturation that it could choose to resolve or not, but that's about the best you can do. For AC is better, it is decidable. It's E-space complete, which is kind of sounds bad in terms of complexity wise, but it's the doubly exponential blow up in egress makes them E-space technically. And more importantly is that you hope anyway that you can solve common cases involving the AC word problem faster than E space, then this sort of upper bound would apply. Whereas E graphs sort of have to chug along to saturation. E graphs with ordinary quality saturation just have to chug along to saturation to be certain that there's no sort of extra critical pairs. Whereas here we can determine that much faster if we have some sort of AC solver. Yeah, any questions? I've got to have another drink. Okay. So actually solving the AC word problem. It isn't, I mean, the base idea isn't too hard. And the idea is if you had two rewrites like this, you find some overlap, which is some term that could rewrite two ways, and you throw out any trivial overlaps where there's actually no part of these terms that is actually shared, right? So you find some pair of terms that have some non-trivial overlap, reduce the sort of middle term as far as you can by existing rules, and then that gives you an equation between between the left and the right, and then add it as a new rule if that final equation is non-trivial, right? It's very similar to what is known as Book-Berger's algorithm, which I will mention later. When we talk more about Book-Berger's algorithm, that's sort of phrased in terms of polynomials, where what we're calling plus is going to be written in time, so that's just something to keep in mind. So here's like an example, right? So this is something I've actually implemented. Here's some starting graph. We have these numbers don't mean, I think 0 is, anyway, so these numbers are just some E-class numbers. But anyway, so we have these two equate, this represents an equation, right? It's two plus nodes in the same class, and running to completion, you get this, which is better than you might get with some sort of a naive doubly exponential equality saturation. Although there is obviously some to get a sort of complete running to AC completion is still some factor of blow up. It's you have to find all these critical pairs.
Cool question.
Yeah, sure.
So, like, I guess one perhaps bizarre thing that it seems like is happening here, or at least bizarre from the perspective of like if you're coming from egg-log style graph implementations, is that congruence closure rebuilding can add stuff, maybe a lot of stuff. Is that? I mean, am I understanding that correctly? Like AC completion, what happened in the rebuilding phase?
Yeah. So there's actually, like you mentioned, there's sort of new stuff that's added, right? There is still an upper bound on this. It relates to sort of Dixon's lemma, which is, I mean, it's like you have to go through the proof to sort of understand why there's upper bound. But I mean, basically, it's because you can't have if you imagine some infinite chain of adding stuff, then there would be some sort of you couldn't build an infinite chain of extra E classes, basically, because there would be some part of it that would eventually reduce using some other part.
Right.
But yeah, it does add stuff. That is, I guess, one thing to keep in mind. Yeah.
But for example, if we were trying to complete the E-graph, then perhaps
there's no bound. Yeah.
Okay.
Yeah.
All right. Okay.
That is essentially why it's undecidable. There's no bound on the intermediate terms that can be generated.
I mean, this is very interesting. Like one of the one thing that this makes me think of right off the bat is that like I mean, equality saturation is terrible at these problems as it stands. So any improvement is welcome. But one interesting side effect is that rebuilding is currently considered a very safe operation in the sense that I believe it will only ever shrink your E-graph, and that's typically very nice. And so we're sort of trading. We're one way. I mean, rebuilding, as you've stated, right? Like, is the theory procedure. It's the canonicalization. It's the the part that's actually has some intelligence to it, compared
Yeah,
to the egraph rewriting part. And so by taking our AC rewrites and shoving them into the rebuilding procedure, the canonicalization procedure, uh, like a lot is gained. But it's interesting to sort of think about how you
yeah, it's,
might have another engineering problem in terms of like
mm,
wanting to manage
yeah.
how
I
much
can,
time you spend in that.
I mean, I can definitely imagine having some sort of like layered approach where you can sort of run congruence closure, not AC, the not AC version,
Yeah.
as its own guaranteed to be guaranteed to shrink the graph step, and then you would have some other call which you could rebuild the AC part, which would
Mm,
perhaps grow the graph, and then the final layer on top of that would of course be the equality saturation, which just sort of does whatever.
yeah.
um, yeah,
Okay. Very interesting.
yeah. So the polynomial encoding. I mean, basically, if sorry, I think this should have pluses here, but anyway, so the plus become times basically. You encode it as this sort of equation, right? You give one variable to each e class, and anyway, so encoding as polynomials is not overkill in the sense that we still have the same e space lower bound for solving these equations, and then it connects nicely to algebraic notions, polynomial ideals, and finding bases for those ideals. Yeah, as I mentioned on my slide, algebraists have been doing this for a long time. It's known as Buchberger's algorithm and Grosvenor bases. Yeah, so that's a connection with a nice word problem. Yeah, I probably don't need to go over the example, but so yeah, so there's sort of refined versions of Buchberger's algorithm as well, F4 and F5, I think they're called, and they're not too hard to integrate with an E-class system, I don't think. So there's one thing that I think the eGraph community has not really noticed, that this sort of congruence closure mod AC has already been discussed in the rewriting world. For instance, by Tawari in his dissertation. So yeah, yeah. So I don't think we've sort of yet to fully absorb all of the insights of the term rewriting world, because
Mm,
rewriting mod AC and congruence closure mod AC have already been sort of well discussed problems. So in that sense, a lot of what I've discussed is not new, not particularly new per se. Also, I mean, Tuari gives methods to you can not just solve AC, but brings polynomials ACU with similar techniques essentially. In terms of getting better than this sort of E-space bound, abelian groups can be solved with Hermit normal form, which is polynomial time, and vector spaces over a field. You can solve with Gaussian elimination, solve the word problem with Gaussian elimination, which is not just polynomial time, but sort of a well-studied problem with quite a tight bound, right? I'm not going to talk about matching modulo AC today. I mean, even though I have ideas, I want to actually make sure that my implementation works out fully before I mentioned I probably won't even have time to talk about this at eGraphs 2026, but I should talk about it in my thesis. So stay tuned for that. But one thing I wanted to mention is integrating theories and eGraphs. There's some sort of design choices here, right? So one is the sort of integrated idea. You treat our plus nodes, our theory nodes, as any other eGraph node and scan for critical pairs somehow. The other method is sort of, you have a side table, don't store plus nodes at all in the normal eGraph, have some sort of side table of AC rewriting rules, right? So when you would go to add E1 plus E2, create a new rewrite rule like this for some fresh E3, and whenever you discover an E-write that is between two atoms and the AC part in the AC side table, you just feed it back into the original eGraph. I chose option 2 for my current implementation. I didn't even really think about this trade-off, but it's there's a couple of things that are not so obvious that I thought I should point out. I mean, I thought they were sort of equivalent, obviously, but the side table approach is that that you might accidentally miss if you have a sort of integrated view. And in the side table approach, if you build the rewrite E1 plus E2 to E3, and then you have some other rule that already has E1 plus the E2 in it, right? You can shrink this rule by rewriting the left-hand side down to, right, this E1 and E2 rewrite to E3 here. So compressing like an existing rule with a new one is sort of a textbook part of a bookpicker's algorithm. But that's something you might not think about if you have this sort of what I call the integrated approach, right? So just finding critical pairs is semantically correct, but it misses this compression if you aren't paying attention. So to make the integrated method equivalent to the side table method, you need some ordering between class nodes in the same class, perhaps, and then do some sort of destructive rewriting of the graph. So I haven't worked out this out in details, but I hope to comment more on that in my thesis. So yeah, so sources, just I'm sort of at the end. I'll just briefly go over the sources and then we can do questions. So Ashish Tiwari's dissertation already mentions a lot of the stuff, and Kapur has also done work on congruence closure mod AC, and yeah, that's the source for the complexity space completeness of the word problem for commutative semigroups. But yeah, I found there is quite a lot more than what I've got here in the rewriting literature that covers you know, things like congruence closure modulo, various kinds of polynomial and so forth. So yeah. So does anyone have any questions?
I have many questions, but I've been asking them. So maybe I'll let, if anyone else would like to cut in front of me.
Yeah,
Now's your chance.
Hey, this is Saul. I just want to say thanks for the great talk. This is really interesting, and for all the pointers to the literature. It's cool to see all this work.
I have tons more, not tons more pointers.
That's
in
great.
My EMT research, it's like so yeah, if you want pointers to the literature, I can give you more as well.
Yeah, and we can also be at the workshop, so maybe we can talk more then. But this is, one question I had was, as I understand it, so the critical pairs piece, this gives you basically more equivalences when you have AC than what you started with necessarily. You just did normal like AC expansion, you wouldn't really get some of these equivalences. Is that the right way to understand this?
So if you use equality saturation with the AC rules, you will eventually find these critical pairs, right? It will do it by running. You'll find some node like this. So if you use equality saturation, it'll see that it'll match A plus B plus C. There's some two nodes in the graph that represent this, right? And it'll rewrite it into A plus brackets B plus C. And then it will discover, and it will rewrite this one into brackets B plus C, and then it'll discover that B and C is sort of shared, you know, and so it will be able to discover this equation eventually via a bunch of different equality saturation steps, right?
I see. Okay.
So in that sense, it's finding all the same equalities as equality saturation, just in a hopefully more efficient way.
Okay, very cool. Thank you so much. Yeah.
I had a question, one of the things that I find I'm like well, I mean, there's many confusing things, but one thing I'm very confused about is the invention of the E constants, because it's like my understanding of like what's in a term rewriting textbook, like they don't talk about this inventing of E constants in order to flatten the thing into the nice flat form.
Yeah.
And I think I have a discomfort that there's like a lot of sins being hidden in that process. Because if you invent enough constants, I think kind of I think there is kind of a nice normal form for even like an AC single flat AC term where you make sure it's always like a binary. You could invent enough constants so it's always binary. And then like you're probably back at like just exploding things out if you invent enough constants. So I just wonder if like the literature has something about that, or you thought about this.
You know,
like
there is
that.
definitely if I go to my slide, abstract congruence closure perspective. Barkmere and others have written on this, and I may think of it as sort of an extended signature, right? So you're extending the signature as you go along, you're adding more constants, basically. Building a convergent term rewriting system on an extended signature. And I have basically like a very sort of deduction rules type presentation of congruence closure, which is just E-graph rebuilding based on this idea, right? Which is yeah. So I don't think there is any, like, to me it doesn't seem like there's any particular sins hiding in inventing new constants. It's just a trick that you can do that helps with certain things. So yeah.
I guess I mean, they may say that, but I think there's sins in there. I think it's not like false. It's not like logically false, but I think if you invent the wrong constants, you're like doing something explosive. And I think kind of like the point is to not materialize stuff. Like you could use regular equality saturation to like materialize all the commutative, all the AC commutative stuff. And if the point is to like not materialize things, and then inventing those constants is materializing things, then like it's kind of an important. Maybe it's an important part of the story, but like controlling that constant creation process.
Yeah, I mean, I guess with my example here, I mean, there's like a bunch of new E classes created, right, as part of the completion. There is still like a bound you can put on how many possible E classes can be created in the process. But it's something Max mentioned as well, that unlike normal congruence closure, yeah, there is this creation of new constants, not just when inserting stuff, but when doing the rebuilding, essentially. Yeah.
Mm-hmm. Well, it's just there's a bound, but the bound of the constants might. I question or wonder if the bounds is basically like you're back to the more naive version. If like it like when you have these multi-nodes of like 1 + 2 + 3 + 4, you're kind of avoiding making those intermediate like naive E-class is, and I don't know, there's just something about that that's like weird. There's something about that that's weird to me.
Yeah.
That's a subjective, like worthless comment, but
okay.
I don't know. I don't know. I wonder if you thought about it.
Yeah, I don't know if I have any great insights here. I mean, yeah, it has to invent some constants, but I mean, I feel like it's as many constants, exactly as many as is needed, right? There's this, we're doing E space worth of work, and that's sort of the best you can do for this problem. Whereas typically you would do double E space, right? Yeah, so I don't know.
I guess sorry to ask another question, but that's a piece that comes up for me when you say how many as needed. I guess how I think about it is like how many as needed is kind of dependent on
it depends on what
you're trying to match against
with
your other rules, like if you need something to show up so that you can match against it, or if you need something to show up so that it's cheaper during extraction, then it's needed. And if not, you don't.
Yeah,
so does the sense of critical pairs at all relate to the rest of your system that you're
does
that make sense?
In terms of, yeah, no, definitely, that's a good point. It does relate to both extraction and matching. But you need to sort of generalize both matching and extraction to sort of work up to the theory. I won't mention, I don't think I have time to mention extraction of my thesis, but there should be a section on matching. So yeah.
I should have prefaced my comment with like awesome talk, by the way, like really good.
Okay, thanks.
Rather than getting to like my little pet peeve.
I have a potentially related question. So if you have other theories that interact with AC, for example, if you have a multiplication that distribute over addition, right? And then once you saturate by that, wouldn't that also blow up the E graph?
Potentially. So you can, the theory of multiplication interacting with it, distributing over addition, is you can use the same Buchberger's type techniques to deal with that. So I mean, I just mentioned Buchberger's for AC in this talk, but there's sort of a generalization that can handle some more complex versions, such as an associative commutative operator with another one that distributes over it, right? So, but yeah, here's some other operator that has some theory that's not particularly well behaved per se. You might get some sort of blow up in saturation, whereas you can imagine it would sort of go through each node and just expand everything out that would otherwise have remained compressed. So yeah, I guess I don't have any examples off the top of my head of that, but I could imagine it being possible. So
thanks.
I have one question that it seems like it may be what Saul already asked, but I'll give it my own spin.
yeah.
It sounds like you'll dig more into this in the matching part. But I guess like my question is like how should I phrase this? Yeah, I guess this is really the same as Saul's question, right? Like we are trying to get away with having some things represented implicitly or canonicalizing them. And there is, I guess I have a worry that like, what if someone is looking for the wrong version of this, right? Now in normal completion, like Knut-Bendix completion, like we have all of our rewrites like sitting right there in front of us. And if anyone is looking for the bad thing, we change them so they look for the good thing. Like we mess with the left-hand sides of rewrites. And I guess like, is that an ingredient in your picture of matching, or is there some other solution that or some other direction that you're thinking of?
So I think the version of matching that I have should find all the matches that matching on the non-modular theories, but with equality saturation would find is I think what I'm aiming for, and I think I can achieve that. So, but like I said, I feel like it's a bit hand wavy until I've actually got an implementation working. So, yeah, hopefully I'll go more into detail in my thesis and my actual written thesis. So,
totally. I have one more question, and this is a very difficult question. But I think one very awesome thing about this line of work is you're grabbing all of these great insights from the literature that have been missed and making them happen in these equality saturation tooling situations, which is awesome. And I wonder if there's room to go even further, right? And Saul was kind of hinting at this in a lot of equality saturation situations. We are not interested in exploring all versions reachable by some set of rewrites, and in many cases we're not even like trying to decide the equivalence of two terms. Like it's not the word problem. We really have some cost function, and in many cases this cost function is quite well behaved and might resemble something that looks a little bit like a term ordering that you would use in Knut-Bendix. And I'm wondering, like, is there a way that we can like jump to the finish line? Or is there literature that we can use here then in terms of like saying like, oh, I know based on all of my rewrites and all of my cost functions and all of this, stuff that like I need to go this way and not that way, right? Like sort of fusing extraction and exploration. So where should we look for that?
I mean, aside from just digging around in the term rewriting literature, I do have some thoughts on this, but I guess you might have to wait for several months for me to put something together. I mean, when doing this project, I had some sort of insight that congruence closure, egraph analysis, egraph extraction, they're all sort of doing the same thing. There's some sort of like weighted rewriting system idea. So eventually I hope to find some time to write that idea up and see how many things I can sort of smush into one framework. Hopefully if you do that, you can kind of you can sort of put the pieces together. If you see it, if they're all the same kind of thing, then you can sort of fuse them together in some way. But yeah, I will need much more time probably to flesh that out. So yeah.
So another, maybe stress-inducing question is, when can we expect to see your thesis?
So it's supposed to be done by June, so early June.
Great.
So yeah, it should be. I don't know exactly how Chalmers publishes stuff, but I mean, I can circulate the PDF version once I've done the final like opposition and stuff. So that will be like early June probably.
Awesome.
Yeah.
Well, are there any other questions from folks? Otherwise, we could wrap up. Okay. Well, thank you so much for the talk, Sophia. And Sophia will be presenting similar but differently flavored and much shorter presentation at the eGraphs workshop, so we can all look forward to that. Yeah, thanks again, Sophia.
Okay.